So does anybody want a quick walkthrough of how PyTorch works, so to speak? Yeah? Okay. So say you've got some data. Your data is X, you've got your label Y. You feed your data into a model. So this model you're going to instantiate from a class. The class here is called DOS classifier. So you come up with an instance of this model. Then you input your data into that model. It's going to output some value, a prediction. We then compare that prediction with the truth. That is your loss. I'm leaving some stuff out. So then we send that loss backwards. So what that really means is you're sending it through the gradients. And the optimizer then makes an adjustment to the parameters based on that loss. So it really is, just think about it, that if anybody's never done deep learning before, it's not as scary as you think it is. It's just linear regression, but with extra fancy steps. So you have some input, you do linear regression on it, on that input multiple times for every hidden unit. And then for every one of those hidden units, you put it through a nonlinear function. And that's what is part of the magic, right? So a nonlinear function here could be like a tanh, or something that's called a ReLU, which just means anything that is coming out negative, we just set it to 0. So you do that a bunch of times. At the end, it's going to have an output. We're comparing that to the truth. It's going to be way off. So we just send the signal back saying, you're off. Go fix yourself this much. But you don't want to oversell it. So you have a learning rate. That means you kind of reduce the amount of correction that's going back to the model because you don't want to overcorrect. So you're going to just learn how to make this neural net train. It's very simple. It's at the end of it. But if you have any questions at all, there are no dumb questions, just dumb teachers. So please feel free to ask. Yeah, we were all in your position at one point if you've never done this before. I've never taught a workshop before, but I've TA'd.
So there's a question Nick asked again.
Yeah.
Following up on the previous one about imperfect data and perfect result. He says, if you have a new model, do you usually look backward to see if there is any fraud you might have missed?
Oh.
So,
No.
yes, we do.
Yeah, but a new model?
Yeah, any new model we backtest on the previous one.
Okay. But no, that you would have missed that had never been caught before?
Yeah.
Really?
Yeah. But also just FYI, there is the fraud landscape and cybersecurity landscape changes very quickly. With any model you try and train to detect new things, the fraudster or attackers find a new way to attack and bypass that thing, right? That's the beauty of machine learning in cybersecurity and digital realm, right? So it's like we train our model based on previous behavior of attackers or fraudster, right? Yep. And and it changes very fast. We try to make our models in the way that adapt and learn and evolve, but every day something new comes up and you have to try to detect the new models based on that. So we always miss something. That's a fact.
Yeah, like an example would be.
Otherwise, we wouldn't have job after a while.
No, that's true. An example would be like gas stations were rife with fraud. 10, 15 years ago in Canada, maybe less. I moved here 12. But I think they were even still a big problem, and are still a problem actually in the States. Whereas over here, you were more likely to see cards getting stolen in large breaches. Say somebody hacks into a database of a company that is storing credit cards and hasn't bothered to hash them or anything, or somebody has compromised a point of sale terminal. Even now, it's getting worse that they're injecting code into third-party websites that are affiliated with another website where you're making a purchase. So for example, it could be an ad company, or it could be a chatbot. And that malware is actually doing keylogging and it's grabbing your credentials as you're typing them in real time. And that's really difficult to tell, because if it's done through a third party, then that gets distributed across all of these different merchants. So it can become a real problem. So it's a real interesting cat and mouse game, for sure. Okay, so yeah, we may as well get started with the code if you haven't already. The first part is really just learning how to train your neural network. I'd say in about 5-10 minutes, I'll show you the real code if you want to wait until then. Okay, so for those in the live stream, now with what had to be filled out, there was just a few little things, but some might have been trickier than others depending on your knowledge of pandas and pytorch. So the first thing we wanted to do was filter for benign traffic and DOS attacks. So we're really only interested in DOS and normal features in the attack category. Once you've filtered that, we can print the ratio. That's not very important, but it's good to know. Then we want to do the train test split. So important thing to note here is we're only looking at the 7 features that we care about. So this is duration, send packets, destination packets, interpacket arrival time, and label. Okay, so once we have done that split, we're going to take the NumPy matrices and then turn them into tensors for pytorch. Okay, and then also use the data loader, which is going to be feeding in batches into the model, batch at a time. So this is the model, very basic, simple to use. And then we're actually going to go and train the model. So we instantiate the model very easily, so it's just doing DOS classifier. You want to send it to a GPU, so .2 device is necessary here, because you're also sending your tensors to the device, as you would have seen somewhere here, I believe. Oh no, that's actually going to be later. Okay, so then we come up with our optimizer. So the optimizer's arguments, we're going to use Atom, but the arguments are going to be the parameters of the model and the learning rate. Now, as we're training, we go through it one batch at a time. From each batch, you're going to have the training data and the labels. The training data you're going to send to the device, the labels you're going to send to the device. Now, each training step, you want to zero out the gradients so that you're not accruing any errors that the model is supposed to pay attention to. So you start with a clean slate every time. So you zero the gradients. Then you're going to get your outputs from the model. Then you're going to calculate your loss. Here I'm using the binary focal loss, so you're comparing the outputs with the truth, the labels. Then we send that loss backwards, and then we take a step forward with the optimizer. So here the optimizer is making a change to the actual parameters. And the rest is just code just to plot things out. At the end, you should have something that kind of looks a little bit like this. We should then save the dictionary of the states of the parameters. This is actually really important for part 2. And I feel like we're not really going to get a whole lot of part 2 covered today, so this is unfortunate. But anyway, it's my own fault. Okay, so predict our values, and we can plot different things. So here's a rock curve. We can look at confusion matrix. We can look at the distribution of what it's predicting. Or my screen can freeze, yeah. Or we can look at the precision recall curve. Okay. Okay. All right. So I'm just going to scroll back up to the training of the model, and then I'm going to go around and help people with questions. But if you have questions yourselves, anybody online, please throw it up in the Slack channel. Okay. Yeah.
If you come down, like if you look at the your loss plot,
yeah,
loss function, right? So like for me or for Behna or for all of us, it's the different values. You want to describe why it's so random?
So why do you get different values on the y-axis?
It's not even the value, like it's the shape was completely
different. Okay, the shape could be a problem. So you can get different values depending on what your hyperparameters are for if you're using, say, focal loss versus binary cross entropy. This is because the focal loss is going to squish the loss function. You're going to get much smaller loss values, but it's all about relativity here. You should be seeing a curve that more or less goes down like this.
At first, I got like two separate curves just bouncing. I reran it, and then now I'm getting this.
Yeah.
At first, it was just
Like look at mine. Like mine is.
If it was going crazy initially,
I just ran your code. Right?
yeah, well that's fine. Like it's never going to be exactly the same every time, right?
Yeah.
So
you describe by
okay, it's not going to be exactly the same every time because you might have different initializations every time. Atom itself has some randomness to it in how it does the optimization. The batches should be the same every time, so that wouldn't be a problem. But I think it's mainly just the Atom optimizer. A lot of it is actually just a slight bit of randomness in how the momentum aspect of it drives the optimizer forward through the loss curve. I hope that's a good enough answer.
Yeah.
And you work with base, right? Is it like you work with? If like generally in fitting, if you're initial.
Okay. All right, guys. So it's not a whole lot of time left, and I did exactly what Amir told me not to do, which was to give you way too much work to work with. I'm sure he'll yell at me afterwards. However, I hope that this is something that you can play with throughout the week. Go home, have a poke around with it, see what interests you. This is not an advertisement for PyTorch and telling you that you need PyTorch in cybersecurity. You clearly don't. Next week will have nothing to do with PyTorch, I promise. I hope. Next week it will be XGBoost. So if you're familiar with XGBoost, great. If you're not, please read up on it a little bit. It's not hard. It's actually a really great model for classification. Yeah, significantly easier than GANs, yes. Good. That's good. I'm getting heckling now.
The hardest one
Yeah.
and then go down from
Yeah.
there.
This is just to thin the hair, right? No, okay, so let's just quickly talk about the adversarial domain adaptation. So I've had a couple of questions regarding like, why don't we use something like transfer learning or something to this effect? And the answer really is that the idea is that you don't have labels for this target data. Here you do, and that's to help you understand how this works. But in reality, you would not have labels to deal with. So if you train this, so if we, so what we're doing here in this cell is that, and sorry, I know that some people in the, so there's a live stream, but some people aren't watching the live stream. This is confusing me. Okay.
Sorry, it's
all right, so in the first cell.
Sorry, you can, in general, live stream the source of truth. If now.
Okay, no, sure.
No.
Okay, so in the first cell of the adversarial domain adaptation section, we're declaring the source model by importing in the parameters that we have saved from the trained model. And then we're also declaring the target model. And we're also freezing the parameters for the source model so that it doesn't retrain. Then this is just a very simple discriminator for the domain adaptation. This is a complicated function, but all it really does is it prevents the model from changing parameters so much that the loss function is going to give a massive spike, right? So, well, actually, no, it's really more that you want to make sure that your gradient doesn't get too vertical. You're not getting exploding gradients, is what this really is trying to deal with. So if you just train this without any of these extra crutches, it's not going to do very well, especially if your learning rates aren't fairly precise. So here I've got a learning rate of 2 times 20 to the power of -4, and here I've got a learning rate of 10 to the power of -4. If you have these too high, they're going to jump all over the shop. If you have it too low, you're going to be waiting till the end of the ice age. So it's a question of making sure you get the right values. I'm using gradient penalty, like I said, to avoid exploding gradients. I found that this was roughly the right parameter to use, hyperparameter to kind of tune that. There's another thing that I used, which I think is kind of weird, but it seems to work. And that is okay, there's a problem with the target model that oftentimes it'll end up predicting values in a very, very narrow range, generally near 0 or generally or near 1. And this is a real problem because you don't want a model that always predicts the same value no matter what it sees. So I came up with a loss function that might not make sense, but I think it does, where I look at the variance of the outputs of this model, and I just get the inverse of that. So if your variance is very, very small, it's going to get a large loss. And if your variance is very wide, it's going to get relatively a much smaller loss. So I feed that back in to the target model as well. So the target model is now not just only looking at the discriminator loss, but it also has this variance loss. And meanwhile, the discriminator model no longer just has this cross-entropy loss, but it also has this gradient penalty loss to ensure that you don't get exploding gradients. So this is the problem that with GANs is that it's kind of an unstable min-max game, and you need to figure out what's the right way to coax the model into behaving. So the last thing I'm going to say really about this is that what I found most striking out of all of this, the thing that seemed to lead to the most consistent performance in the target model was actually the source model to begin with. So yes, having a stable GAN, or at least something that's approaching a stable GAN, is very, very important. But having a source model that's susceptible towards generalization, that isn't too overfitted to its training data, is key. It's absolutely vital here. It's I don't know what it is, but I came across one source model that led to the target model behaving much better consistently every time I trained it. So I can't tell you exactly why, other than it should just be a source model that is well generalizable, so it's not overfit to the training data. How you go about and ensure that is up to you. But these are thoughts of a crazy person who's been dealing with this for the past few weeks and trying to get this to behave. So there's a lot to cover today. We're obviously not going to cover everything. I do really encourage you to go home and play with this. Like I said, Collab is free to use, but if you have your own resources, then use them there. The full document is in the folder, so you can just play off of that. And feel free to fix my code if there's things you don't like, such as reusing the same parameter or reusing the same variable names. Does anybody have any questions, either online or elsewhere? I just realized I'd muted this the whole time. Okay. Okay, yeah.
I'm guessing the paper I didn't see the paper yet. This, the domain transfer thing. But is the loss functions, what made you decide to add that to the loss functions? Is it like versus like what the paper has shown? Like, is it more unstable in the paper, like for their examples?
Yeah. No, I think it's a good question. So there's a couple of papers. There's one that dealt with the DOS stuff, but they didn't go into too much detail, other than said it's really hard. And the original paper, the adversarial domain adaptation paper, deals with MNIST. So it's a different data set. And I think it's a lot more stable and a lot easier to deal with. But the gradient penalty is a common approach to deal with GANs. So that's normal. And the variance thing is just something I came up with because I kept on seeing that it was giving this narrow output for the classification with the target model, and this was a problem because you need it to be broad. You need a lot of zeros and a few ones. So that's what I decided would help. Okay.
Oh, but then that variance with that. Sorry, no, never mind. I was just thinking. If there, like, say for like, you are in an example where you have very little, like sort of fraud detection, where you just have very little cases of positive results. Would that be would that hinder? Would
So as you're saying, as the ratio of positive or of negative to positive results goes down, goes to 0, how does that affect the output distribution?
yeah.
It pushes it towards the edges. Depending on if it's not a good model, if it's not robust towards like imbalance, you will end up probably getting all your parameters getting pushed, or the outputs getting pushed towards 0 or pushed towards a 1. So you have to account for that imbalance as best you can. Yeah.
The idea of transfer learning, right? Okay, so I mean, we're now dealing with a problem. This is, we said, attacks, right? Attacks on a server or attacks?
Domain denial of service attacks. Yeah.
Right. Okay. So, how about, for example, if you take like a problem which is similar to it, maybe attacks on, I don't know, on laptops, attacks on websites and so on, which could be maybe more better data, and you train, let's say, CNN, like fully connected layers, whatever, right?
Yeah.
And you extract the weights from that, and then you make that the starter of your GAN, with maybe a couple of fully connected layers, and then do at the end the classification. Well, would that work? Like the idea of extracting weights from a problem which is similar to it.
Yeah. Okay, so I'm going to say no, and I'll say why, but then I'll also say that what you're suggesting raises a good point about how you might augment this further. So no, it won't, because there's no... You can't really say that there's a joint probability distribution like that. How do I say this? So that basically any of these features co-occur. Any of the features that describe this type of attack would co-occur with these features that describe this attack. At some point, if they are going to start co-occurring, well, they are probably just the same attack. So it's not going to be informative for the model for it to see attacks from some other domain, from some other problem, right? It should still be within the same domain itself. You've got enough trouble trying to ensure that you're covering the entire domain of DOS attacks. Trying to solve it by bringing in something else, like, I don't know, like somebody doing a SQL injection or something like that, that's not going to work.
Just like the other day, I heard about this company in China. Like they want to replace, for example, the rear mirror in your car, right?
Yeah.
So you can talk, hey mirror, show me the car before, like behind me, right? So they didn't have tons of data. What they did is they just retrieved like the Google Home and Echo from Amazon. Like they want to say hi Google and so on. They bought this data. So and then they just got all the weights from those training and feed it to their network, and then it worked. So at the end, they now train the model, right? Which can talk to you can talk to the mirror based on weights that they started from Echo, from Google, from all these different devices, right?
But that's still all the same domain problem there, right?
Right.
So it's not. There's differences, but it's almost like an ensemble or something. Like it's not really the same. But like I said, you raise a good point in that. So in trying to get an intersection between the source and target data, one of the things I was trying to illustrate there was that it's difficult to even find features that they have in common. And so we were only able to find 7 features in common, and that actually crippled your source model to begin with, because you're throwing out all of these other features, like about 30 features you're just throwing out, right? And these can be really informative. So one thing I'm wondering if it's possible, I don't know if it is, but you could have a multimodal model where you have in one mode, you have the 7 intersecting features between the two models. In the other mode, you have all the other features, the auxiliary features for the source model, and then you train the source model. Hopefully, with this co-occurrence of features from the auxiliary set or mode with co-occurring with the features from the core mode, it might help the model learn that this feature is really important, that I need to pay attention to that. Especially if you did something use something like dropout very strongly, or you switch the channels on and off to make it dependent, not so dependent on them both being there. And then with the target data, just feed through into this mode and ignore this mode. And you might get a better improvement then, because you're also limited in the performance of the target model by the performance of the source model. Having said that, so while you are limited in terms of the training and validation data, what I found was really interesting here is the target data is getting an F1 score that is better than the test data for the source model. So that means that the test data for the source model is so diverged from the source training data that it's really challenging for the source model. But it's actually true that the target model, for some reason, target data is actually closer to the training data of the source model than the test data is, for some bizarre reason. So the point I'm trying to make is that you can actually get really good performance with this adversarial domain adaptation, and it's limited by the performance of the source model, but if you improve the performance of the source model, then maybe you can improve the performance of the target model as well. Okay, rant over, yes?
For this extra thing that you added for the loss function, the pred spread.
Yeah.
I'm just like looking through the code, like it's getting updated in the backward propagation, but like how is it added to the loss? Like, is it just for your information you're looking at it, or
no?
It's just
so you do dot backward, and that. So loss doesn't necessarily have to correspond to the labels. It can correspond to any kind of function you want it to, so long as, again, that loss function is differentiable and the model itself is differentiable. Okay, then you can send the loss backwards.
Okay, so maybe my question is like how this is contributing to the loss spread.
So
Can you repeat the question? I didn't.
Sorry. So how is the spread, the function that I've come up with, this loss function that looks at the variance in the target output, how does that contribute to the loss? So what I'm trying to say here is that the loss function can be any function so long as part of that function is output of the model. So the output here is going to be the
variance of the...
Oh shit, yeah, actually there might be a problem there though. Yep, I think you've actually caught something there. I should be looking at the variance of the last layer and not of the classifier. Because
thinking that complicated.
Yeah, but I think actually I was too smart. So
like just from what I'm seeing, I don't see it like how it's a.
Is there there should be a line that says.
So yeah, here is a
spreads up backward. Yeah.
So that will that kind of contributes to the loss.
Yeah.
Okay. Okay.
Yeah. I think I still get away with it because it's only a sigma function. But yeah. So Amir is standing.
I usually stand. So
Okay. you looked expectant.
I always expect.
Yeah.
But whenever you're done, I want to come here and
Okay.
talk to people.
Okay. So.
We need at least 3 more hours for this to finish, but.
In conclusion, yeah, the GAN is probably going to be homework for you guys. Please play around with it. Amir wants to say a few words, and thank you all for coming.
Close your labs, please.
Yeah, please come next week. It'll be a lot easier. And really, I appreciate all the questions you have. I live for questions. I live for skepticism and criticism as well. So please, yeah, please give me feedback. And if you're struggling or whatever, just help me understand. Okay.